right, Organic Chemistry 1. This is Chapter 15, which deals with NMR, or Nuclear Magnetic Resonance Spectroscopy. And before we get into it, I want to explain to you, what the whole point behind this chapter is, or give you an idea of what the point is. Let's say we had a compound with a formula that is, let's say, C4H10O, okay? So 4 carbons, 10 hydrogens, and 1 oxygen. Let's say we had this compound, so this is diethyl ether. It's commonly used as a solvent in organic chemistry. And if we had this compound, this is called 1-butanol. Based off of what I've taught you thus far in the class, could you use spectroscopy to determine which compound is which? And the answer is absolutely you could, right? A couple of ways. I mean, first of all, we know that the mass spec of an alcohol would be different than that of an ether, but I think even easier would be to use infrared spectroscopy, right? Because if we use infrared spectroscopy, I mean, we're going to see the strong absorbance for the oxygen-hydrogen bond, around what? Anywhere from 3,200 reciprocal centimeters, down to 28 or whatever. But we're going to see that broad oxygen-hydrogen stretch, whereas we wouldn't see that with an ether. So we could use infrared spectroscopy to differentiate between these compounds rather easily. But what if I had compounds with the same molecular formula? So still going with that compound, what if I had this first compound that is written above, and what if I had an isomer of it, right? What if I had the hydroxyl in this position, or what if I had something that was like this? All 3 of these compounds, they're all alcohols, and so it would be very difficult to differentiate between these 3 compounds using mass spectrometry or using infrared spectroscopy, because they all have the exact same functional group. But you can see that all 3 of these molecules have very different connectivities, don't they? Right here I have, CH2, 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 CH3. Here I have 2 methyl groups, right? In my molecule, I have a methylene and a methyne. And in the last one, we have 3 methyl groups. And so again, the connectivity of all 3 of these molecules is very different. And that's the whole point behind nuclear magnetic resonance spectroscopy, is that we could very quickly use NMR to differentiate between these 3 compounds because their connectivity is different. And that's what we're going to do, is we're going to learn how to differentiate between molecules like that using the technique of nuclear magnetic resonance spectroscopy. So NMR, or nuclear magnetic resonance spectroscopy, is, again, I mentioned this earlier to you before I started recording this video. It's probably the most powerful method that we have to gain structural information about organic compounds. If you were to take an organic chemist from 2021 and put them back in history without NMR, it would be pretty tough for that chemist to survive, right? We've become so dependent on this technique because it is so powerful. And the difference between, spectroscopy of NMR spectroscopy and infrared spectroscopy is that spectroscopy is the interaction between electromagnetic radiation and matter. However, in IR, we looked at the interaction between infrared light and bonds in functional groups, whereas in NMR, we look at the interaction between electromagnetic radiation in the radio frequency range and the interaction between it and the nucleus of an atom. So that's where the N comes from, right? Nuclear. We're talking about nuclei. We're not talking about bonds. So what are the nuclei that we're going to focus on in organic chemistry? Well, the good news is that we're going to focus on carbon and hydrogen, which are pretty much present in all organic compounds, right? We always have carbon and hydrogens, carbon-hydrogen bonds, but we find hydrogens in virtually all organic molecules, and carbon, obviously, we always find that. And so what are we going to do in NMR? And I've already alluded to this, is that we're going to determine the connectivity of the molecule. And the good news is that the connectivity of the molecule, the way the molecule is put together, is going to affect how the electromagnetic radiation, again, which I told you is in the radio frequency range, how it's going to interact with each of the nuclei in our molecule. So again, the interaction between light in the radio frequency range, right? We can't see it with the naked eye. We know it exists, okay? And it's the interaction between that type of electromagnetic radiation with nuclei of a proton or a carbon. So it says here that protons and neutrons in a nucleus behave as if they are spinning. They are not spinning like a top, but it is a very useful analogy, and so that's how we're going to treat them, right? We treat them like they're spinning around and around. And when we have an atom that has an odd number of protons and or neutrons in the nucleus, it possesses a property called net nuclear spin. So what have we got? We've got a nucleus in an atom. It's got an odd number of protons and or an odd number of neutrons, and it's spinning, right? We imagine it spinning like a top. And what are some examples of nuclei that possess net nuclear spin? Things like hydrogen 1, which is just a regular proton, carbon 13, which is an isotope of carbon, remember, and you may not remember this, but I'll just refresh your memory from general chemistry and from organic chemistry that most carbons are carbon 12. That's the most abundant isotope of carbon. It makes up about 99% of carbons, roughly, and around 1% of carbons are carbon 13. Okay, then we have other nuclei like nitrogen 15, fluorine 19, and phosphorus 31. We're not going to talk about nitrogen, phosphorus, or fluorine NMR in this class at all, but we're going to stick to proton and carbon 13 NMR spectroscopy. Now, we've got these nuclei, whether it be a proton or a carbon. Now, if that proton or that carbon nucleus has this property called net nuclear spin, what happens is if the nucleus has a charge, which it does, right? It's got a positive charge. All nuclei are positively charged. If you have a spinning charge, what it does is it creates a little magnetic field, okay? A little tiny magnetic field, and we call that magnetic field a magnetic moment. So again, what have we got? We've got a nucleus that's spinning around. So here's our nucleus right here. Again, we're imagining it spinning like a top, and when it spins around and around, and you see it spinning here on this axis, right? It's spinning around and around. It makes this little magnetic field, okay? Just like a bar magnet does, okay? And I'm sure that everybody or most of you have played with a bar magnet at some point in your life, okay? And you've seen how, you could take iron filings on a piece of paper, on top of a bar magnet, and it makes these little magnetic field lines. All right, but you see how the magnetic field lines, you see how their direction is going like this and like this, then it goes up, right? They're going up in this direction, okay? And then they come back around like this, right? And then they go back up like that. But those are the magnetic field lines of our spinning nucleus. Now, there's something missing here in our atom, right? If this is the nucleus, we know that a nucleus is surrounded by what? Electrons. So we don't have electrons in here yet. We're just talking about the spinning nuclei. Now, what's interesting about these spinning nuclei is that if you just think of all the different nuclei that you have in an organic compound, right? You've got all these proton and carbon nuclei. Well, normally all those little magnetic fields, those little magnetic moments, they're normally all just randomly, pointing in whatever direction. Okay, so again, you have a sample of an organic compound. The nuclei are spinning. Okay, they're creating this little magnetic field, but all these magnetic fields are just pointing in random. They're pointing in any direction. Okay, any direction at all. But here's where it gets kind of cool. If you subject all those normally disordered magnetic moments to an external magnetic field, in the magnetic field, we couldn't use the letter M. That's too easy, right? We have to use the letter B to represent our magnetic field. So we use B0, or sometimes I'll call that B naught. That means that's our external magnetic field, right? That's the M in nuclear magnetic, okay? We subject the organic compound to an external magnetic field, and what happens is that all of those magnetic moments, those little tiny magnetic fields, they get affected by that externally applied magnetic field, and they align. It's like they're coming to attention, kind of, like ping, you subject it to a magnetic field, and then all of a sudden, all of the magnetic moments will align with the magnetic field. However, they can align with the field, okay? And we call that an alpha spin state, or they can align against the field, and we call that a beta spin state. And you can clearly see that in the picture here on the right-hand side. These field lines here, these blue lines, represent the applied magnetic field. That's the direction of it. You see, again, that some of them are aligned with it. That's what we call an alpha spin state, okay? And when they align against the magnetic field, we call that a beta spin state. So what have we got so far? I'm just going to repeat. We've got nuclei that have an odd number of protons and or an odd number of neutrons. They possess a property called nuclear spin. It's like a spinning top. What happens when you have a charge? This is charged, isn't it? If it spins around, it creates this little magnetic field called a magnetic moment. You take an external magnetic field, you subject the organic compound to that external magnetic field, and the magnetic moments align with or against the magnetic field. If they align with the magnetic field, it's called an alpha spin state. If they align against it, it's called a beta spin state. So that's where we are right here. But what's even cooler is that the interaction between the magnetic moment, the tiny magnetic field of the nucleus, and the magnetic field that's applied, the external magnetic field, it's quantized. Okay, it's quantized, just like we talked about, quantization in quantum mechanics. It's quantized, and the magnetic moment must align either with that magnetic field or against that magnetic field. It's never going to align, askew or anything like that. So the beta spin state, I already told you what that was. It's the spin state that opposes the external magnetic field. Again, the B0 that represents the externally applied magnetic field. So that's just a big magnet that you use to subject the sample to a magnetic field. And the alpha spin state, that is the one that is aligned with the magnetic field. Okay, the alpha spin state is the lower energy spin state, and the beta spin state is called the higher energy spin state. And again, what's really cool is that the difference in energy between these two spin states is quantized. And I'm going to talk more about that later on, what I mean by, the difference in these two spin states, right? There's a high energy, the beta spin state, and there's a lower energy, the alpha spin state. Okay, well, you can obviously see that we don't have all the clues yet to understand, like, why, how do we get an NMR spectrum or anything like that. So we got to keep moving on here. Now, see if you can follow with me. It says when an atom in an alpha spin state, right, the lower energy spin state, is subjected to radio waves, okay, with just the right energy. What's just the right energy? It must be quantized, right? It's got to be a very specific energy, a very specific amount of energy. A photon of light is going to get absorbed, and this alpha spin state can flip up to that higher energy beta spin state. Poof, okay? So again, we're subjecting the molecule to a magnetic field. You have an alpha spin state, a beta spin state, but what's cool is that if you hit the nucleus with an alpha spin state at just the right amount of energy, it's going to flip to a beta spin state, okay? And what else is interesting is that the stronger the magnetic field, the larger the energy gap. So we could write that another way, and we could say that the energy gap, I'll put here the E, is proportional to our magnetic field, okay? So again, this energy gap is going to be dictated by the strength of our magnet, really, okay? And I'll talk more about that as we move along here. All right, there we go. So just let me double check one thing here quickly. Okay, anyhow, I'll introduce the term resonance in a second. But like I told you earlier on, when we were talking about our spinning nucleus, there was something that we left out, which was what? We left out the electrons, right? We didn't mention the electrons at all, okay? Well, what happens is when you subject that nucleus to the externally applied magnetic field, not only does it either have an alpha or a beta spin state, but it also affects the electrons because electrons are charged. So they're going to be affected by the magnetic field. So I'm going to read this right off the slide. It says the externally applied magnetic field, B0 or B naught, causes the electrons to circulate as well. Now that causes another magnetic field, and that magnetic field opposes the applied magnetic field. That is called diamagnetism. And all objects possess this property, and it's talked about a little bit more in our textbook. I'm not going to go into more detail about that. But so see what's happening over here. Now, these field lines that are shown here on this slide are not the same field lines that we saw a few slides ago. Let me back up and prove it to you. If you look at the field lines that I showed you at the very beginning, these ones, okay, you see how they went in this direction, right? And then they came back around like this, okay? Those are the field lines created by what? By the nucleus, by the magnetic moment of the nucleus. Now they've actually decided to show you in the picture, they've left out the field lines of the nucleus, but they're showing the field lines that are produced by the electrons circulating. Okay, so that's what's represented here. These are the electrons circulating around the nucleus, but they create another field. Okay, and you notice that the field is in the opposite direction. Look, you see how the field lines are going down like this. So they're going against the externally applied magnetic field. So you've got the applied magnetic field going in this direction, but the circulating electrons are creating an opposing field, okay, in the opposite direction. That's what opposing means. So now, what's the effect on the nucleus? The nucleus doesn't feel all of that magnet, does it? Right? It doesn't feel all of that magnetic field. It feels a lot of it, but there's also some of it going against it based off of the number of electrons that are around, or the electron density, I should say. So it creates a de-shielding effect, a shielding effect, where it shields the nucleus from the externally applied magnetic field. Okay, so it says nuclei then experience less of the externally applied magnetic field and is said to be shielded. And what the other effect is that it requires less energy to get them to spin flip, to go from the alpha spin state to the beta spin state. So that's what a spin flip is, okay? It's going from the alpha spin state to the beta spin state. So the more electron density that you have around a nucleus, right, the more electrons you have around it, the stronger this opposing field will be, okay? And we say that the more shielded it becomes. So the less electron density that you have around your nucleus, right, then it's going to feel more of this, and you say that it's de-shielded. It's not shielded by the electrons, and then it feels more of the magnetic field, okay? All right, so to summarize, the amount of radio wave energy that's necessary for the alpha, the beta spin flip depends on the electronic environment of the atom, right? Because if you go back here, I told you that the difference in energy between the alpha and the beta spin state is proportional to the amount of the magnetic field, or to the magnetic field. Well, how much of the magnetic field is going to be felt by the nucleus? Okay, that is going to be dictated by the amount of electron density that's surrounded, right? If it's surrounded by a lot of electron density, it's going to be shielded, okay? Then it's going to require less energy to spin flip. If it's surrounded by a lot of electron density, it's going to be de-shielded. Sorry, if it's surrounded by less electron density, it's going to be de-shielded. So again, when the alpha spins are flipped to beta spins, energy gets absorbed, and that's the term resonance. That's what resonance is. So if we go back here again, when you go from the alpha to the beta spin state, that's when we say the nucleus is in resonance. Okay, it's got nothing to do with resonance that we looked at way back in chapter 2. It has nothing to do with that at all. Okay, now we're talking about electrons that are in molecular orbitals. Anyhow, so what's the whole take-home message here? It's that the amount of energy that's required for each proton to spin flip will tell us about its electron environment, right? It's going to tell us about that. So if the nucleus is de-shielded, okay, it's going to feel more of the magnetic field. Therefore, the energy gap is going to be bigger, and it's going to take more energy to make that spin flip occur. If the nucleus is more shielded, it's going to feel less of the magnetic field. The energy gap is going to be smaller, and it takes a lower frequency of electromagnetic radiation to get that spin flip to occur. So there we go. So this is kind of a summary. I added this a couple semesters ago. I didn't have this the first time I taught this chapter. But again, just to summarize, it says, because of its charge and spin, a nucleus behaves like a little magnet. Okay, what Nmr spectroscopy is we just take an externally applied magnetic field, we subject the nuclei to it, and we measure the amount of energy that's required to put the nuclei into resonance, right, which is just the alpha to beta spin flip. And you know, if every single nucleus was in the same electron environment, had the same electronic environment around it, well, then this wouldn't be very useful, would it? Right, because then they would all resonate at the same energy gap, the same field strength, right? But we know that that's not true because they're all in different electronic environments, okay? And so basically what an NMR spectrum that you're going to learn to interpret, all it does is it shows you a signal or a peak representing the amount of energy that's required to bring each nucleus into resonance. And that again tells you about the electronic environment of the nucleus. So getting back into it here and a little bit more on the mechanics of the NMR spectrum. So this is section 15.2. We need a really strong magnetic field in order to run an NMR spectrum. Okay, so strong that people who have pacemakers, for example, cannot go near a spectrometer because it's very dangerous for those people. So we need a really strong magnetic field, and we need radio wave energy. So strong magnetic field and radio wave energy. And again, I told you that the strength of the magnetic field is what affects the energy gap. So you see here that if we have a weaker magnetic field of 1.41 Tesla, then we have a smaller energy gap between the alpha and beta spin states. If we have a larger energy gap, that would be the result of a stronger magnetic field. Now, I'm not going to go into all the details of this, but you need to understand that the difference in energy, again, is proportional to the magnetic field, which you can clearly see on the slide here, but it's also proportional to the frequency, okay, the operating frequency of the spectrometer. And again, I'm not going to go into a lot of detail about that, but sometimes you'll hear me say, you know, higher frequency or whatever, or lower frequency. So the operating frequency of a spectrometer that uses a magnetic field of around 1.41 Tesla, it's going to have an operating frequency of 60 megahertz, which means it's going to pulse or hit the sample with radio wave energy in that range, okay, 60 megahertz. And if you had 7.04 Tesla, that means the frequency of electromagnetic radiation you're going to subject the sample to is going to be higher. It's going to be around 300 megahertz, okay? All right. Well, and if you're wondering, you know, what's the difference between subjecting my sample to, a lower magnetic field versus a higher magnetic field? Well, I can tell you that the higher the magnetic field, the more expensive the spectrometer is, but we get better resolution, and I'll explain that as we move along. Okay, so how do we get these strong magnetic fields, like these very strong magnets that are literally dangerous, you know, if you were to have a pacemaker? Well, it's an electromagnet, and I'm sure many of you have made an electromagnet at some point in your life, where you just take a wire and you wrap it around a nail and then you put a battery to it or something like that. Well, the strong magnets that are used in NMR spectroscopy are generated in pretty much the same way. You take a powerful current and you pass it through a superconducting material, which causes very little resistance to that current, and it just basically makes a really strong current, and you have a really strong magnet. So the greater the current, the greater the magnetic field. Now, what we use nowadays is called a pulsed Fourier transfer spectrometer, which we normally call an FT spectrometer, Fourier Transform. And what we do is we take our NMR sample and we hit it with a pulse of radio energy. So every relevant wavelength that's going to cause the excitation of the sample. Now, excitation of the sample, all that means it's going to cause resonance to occur for every nucleus. So you're going to go from an alpha to a beta spin state. Okay? So again, what we do is we take our sample and we hit it with every dang frequency of radio energy that's required to get every nucleus to flip from alpha to beta spin state. But then what happens is that each of the atoms that was excited is going to relax. Okay? It's going to go back to, or it's going to go from the beta to the alpha spin state, and then it's going to give off energy when it does that. So it's going to go down and it's going to give you energy, and different amounts of energy based off of the amount of energy that was required for the spin flip. So the emitted energy gets recorded as a free induction decay, or an FID, which is way beyond the scope of our class, and then it gets processed through a technique called the Fourier Transform, which is just a complex mathematical treatment. And then what that does is it separates the signals, so each individual signal can be observed for every atom that was excited. And normally we take a bunch of FIDs together. It's usually a multiple of the number 8. So 8, 16, 32, 64, 128, whatever, 256. Anyhow, so before you start running an NMR sample, you've got to prepare the sample in a liquid solution, which is usually a deuterated solvent. Let's say you have a solvent like chloroform, right? CHCl3, that's chloroform. Well, the problem with using chloroform as a solvent is, what's the definition of a solvent? A solvent is present in a larger amount. So chloroform has hydrogen in it. So that means you're going to have mostly CHCl3 and a very little amount of your organic compound that you want to see in your spectrum. And so all you would see is the spectrum of this. So what you do is you replace it with the deuterium and you make CdCl3. Okay, so then you've got, this is called deuterated chloroform or deuterochloroform. And so you might be saying, well, based off of what you told me, Mr. Dion, in deuterium, the nucleus still has one proton and one neutron. So that's an odd number of protons and or neutrons. So doesn't that have spin? Yes, deuterium does have spin. However, it resonates at a frequency that is going to be way different than hydrogen. And so even though your sample is in deuterochloroform, you wouldn't see any of the deuterium. And so it's not going to, cause any, complication. So there you go. So you put the sample in the spectrometer into that high magnetic field, and the tube gets spun around at a high rate to average out magnetic field variations or imperfections in the tube. It's based, and if you're like, what the heck does this mean? All it means is that you just run the sample and you try to minimize any imperfections and you try to make the nicest possible sample that you can. So here is, a figure right out of our textbook. It shows you what a spectrometer looks like. It kind of looks like this. It says it's a superconducting magnet cooled by liquid helium. So inside the spectrometer, it's got like two jackets, right? You have the outer jacket, which is just a vacuum, to prevent heat from being transferred. Then you have the inner one, which is liquid helium, which is around 77 Kelvin. And then on the very inside, you've got your, your liquid nitrogen. Sorry, I'm confused here. You have liquid nitrogen on the outer jacket, and then you have liquid helium on the inside, because liquid helium boils at like around 5 Kelvin or 4.3 Kelvin or something like that. Anyhow, so you can see the temperature in here is really, really cold. You spin the sample around and around, then you have this big, thing here, which is your radio frequency generator, and you send the radio frequencies through these cables, and you subject the sample. So the sample is being subjected to a strong magnetic field, and then you're pulsing it with the radio frequency, electromagnetic radiation. And normally we take our samples at room temperature. You can do temperature variations on NMR, and I'll talk about that briefly. But I just wanted to show you some Google images here for a second. No, not that. Some Google images. So this is an NMR spectrometer. I don't know what university or where this is, but this is, you can see that it says 700 on the side. That indicates the operating frequency. So that would mean this is a 700 megahertz, and you can see the radio frequency generator and the cable there. And it gives you an idea of how big a spectrometer is. Something else, you notice that the tank portion of the spectrometer, and I can't write on this, but you see how there's these like black legs on the side? Well, those legs actually have air cushions in them, and what that does is it minimizes imperfections just in vibrations in the floor. Now, the tube that goes inside this giant, white tank here that's shown here in this spectrometer is actually really small. This is a Google image of an NMR tube. So you can see that the sample dissolved in the solvent is very, very small. And if you go back here, you can see you can buy all kinds of, NMR tubes from a supplier. Here's a sample. The one on the left, somebody put way too much sample in there. The one on the right is the correct amount of sample that you would want to put in your NMR tube. Anyhow, this is an NMR tube washer, this thing here. Anyhow, I think it is anyway. Anyhow, what else do I have here? This is a free induction decay, which is neither here nor there really, but that's what an FID looks like. And then you do the Fourier transform, and it ends up making an NMR spectrum, which is, something that you can actually interpret. And then, this is what a spectrum looks like. So here's a typical organic compound, and this is an organic spectrum. Or an NMR spectrum, and this is something that you will learn how to interpret. This one might be a little complicated for the chemistry 3111 level, but I'd say that this one is not. This is something that we would be able to, understand. This is just an ester here, so this is, something that you'd be able to figure out, or maybe a compound like this, something a little smaller. But there you go. That's what an NMR spectrometer looks like. And again, the higher the operating frequency of the spectrometer, the stronger the magnet and the more expensive they are. So they get more and more costly. Anyhow, and then of course here we have our deuterated solvent, which is required as well to run our sample in. And there are many other types of deuterated solvents out there. So let's talk about the characteristics of an NMR spectrum. I showed you an NMR spectrum on the last Google image, but this is what an NMR spectrum looks like. This is a typical NMR down here. It's a proton NMR. It says you can get a lot of important information from an NMR spectrum. First of all, you get a number of signals. Here we have 1, 2, 3 signals. I know that in each one you can see a bunch of little peaks, but taken together as a collection, this would be signals. We got 3 signals here total on this NMR spectrum. Next, you see what's called the chemical shift. So you notice that chemical shift is the scale that's in parts per million, which is on the bottom of the spectrum here. And that tells you about the electron environment for the proton, because the more de-shielded, so we'll put here de-shielded, the more de-shielded a proton is, so that means the less electron density there is around the proton, the higher chemical shift it's going to have, and the more shielded it is, meaning the more electron density there is around the proton, the lower the chemical shift is going to be. Another thing you see is an integration, which isn't shown on here. Okay, so integration isn't shown, but you saw it in the Google image. If we go back, and I'll show you quickly here, in this NMR spectrum, where was it? The last one, or this one here? All right, if you look at this, oh, son of a gun, you can't tell. I'm trying, if you could see that, but you can't. Crap, here you go. So the integration is a number. So you see by these 2 peaks, it says 1 and 1.5. So let me show you what that would mean here. A lot of times on an NMR spectrum, let's say by this signal, you'd see a number like 5, and then here you'd see a number like 2, and then here you'd see a number like 3. What that indicates, the integration, is the relative number of protons. That means that in this region, we have 5 protons of this type, and or some multiple of it, like 5, 10, 15. Here we have some multiple of 2, so 2, 4, 6, 8, whatever. And then here we have 3, 6, 9, etc. Okay? But if there was exactly 5 protons here, for example, that would mean there's exactly 2 here and exactly 3 here, represented by each of these signals respectively. Then it says multiplicity. So multiplicity is tells us how many adjacent hydrogens we have. So on this peak that's the most shielded, this one here, you can see the chemical shift for this one is right around, if we have 1, 1.1, 1.2, 1.3, it's right around 1.2, let's say. So this is around 1.2 parts per million. Okay. But then you can see that it's a total of 1, 2, 3 little peaks, isn't it? So we would actually call this, a triplet. Okay. A triplet. And the triplet actually gives us information as to how many protons are next door to these 3 protons. Then here, where you see the 2 protons, we have 1, 2, 3, 4 little peaks there. So we call that a quartet. So this would be called a quartet. And again, the quartet tells you something about how many protons are next door. Now, the last one, if you're looking, if you're ahead of me, you can see the last one, it's pretty difficult to tell what's going on. This one, where it's not abundant, how many peaks are here, we would call that a multiplet. Okay, and we'll talk about how to interpret a multiplet later on. But the multiplicity is really important because it tells you how many hydrogens are on adjacent carbons, and we'll get into that a little bit more later on. All right, I don't know how long, come on.